By the way, RSA is going on right now, and if you sign up here, you can go for free on Thursday. I would have gone, but as you can hear, I've got a nasty cold. I don't want to spread it, so I'm teaching everything online and staying away from any public settings like that for a week or so. But you can go on Thursday. It's kind of fun. If you do go, it's worth extra credit in any of my classes. All right. And so this is COMSC 142, and we're near the end of this class. We got chapter 14. Next time I'll do chapter 15, and I won't add any new material on the last day, so that's it. Then comes the final exam. The final exam will only cover chapters 1 through 12, because when I originally planned this class, I wasn't really sure how long it would take me to cover these chapters. So it turned out to be faster than I guessed. And so I made chapter 13, 14, and 15 extra credit. There'll be quizzes you can take, but they're extra credit. It's interesting material, so I think next time I teach it, I'll just have them part of the required material. But the first time I left a little room because it's possible that I'd have to split some of the other chapters in half, and that didn't happen so much. Anyway, so we're up to chapter 14. I'm really glad to learn this stuff. I've never really completely understood what GPUs are doing. So this is helping me learn stuff. I've been hanging around on the edges of it for years, but I never really learned what was going on. I've never programmed a GPU. This makes me think maybe I should give it a shot. I know they're much, much faster, and I have a much better understanding why. So that's what today's topic is: parallel performance, cache coherence, thread safety, and OpenMP, mainly about GPUs. So we'll talk about speed up and some of the theories that led to the current world of multiprocessing. So, speed up is pretty simple. If you run a program on one core, measure how long it takes, then you run it on C cores, you take the time for one over the time C, and that's the speed up. If you cut the time in half, the speed up is 2. If you cut the time in a quarter, the speed up is 4, and so on. So if it takes you 60 seconds to execute on one processor, but 30 seconds on 2 cores, that's a speed up of 2. That's pretty simple and obvious. And pretty obvious, the next thing is the efficiency. So that would be, in a perfect world, doubling the number of cores would have a speed up of 2. And having 4 cores would have a speed up of 4, and so on. That would be if there was no overhead, no waste. Just having more cores meant you get more work done. And that's what the efficiency is. You take the speed up and divide by the number of cores. So if a serial program takes 60 seconds, but a parallel program takes 30 seconds on 2 cores, that's an efficiency of 1. 2 cores give you half the time. But if it takes 4 cores to get to 30 seconds, that's 50% efficiency. You've only gained half of the sort of theoretical maximum. That's pretty obvious too, a simple measurement. All right, now in the real world, of course, you never get that 100% efficiency because there are parts of your code that cannot be serialized. And that's what they call the critical path. The part of your code that requires, for example, one example comes up later. Oh, here it is, the nth Fibonacci number. Remember, the Fibonacci numbers, you have to add the previous 2 numbers in series. So you take 1 and 1, you get 2. Then you take 1 and 2, you get 3. Then you take 2 and 3, you get 5. So you can't calculate the next number until you have the numbers before it. So you can't parallelize this job. You can't start one processor at Fibonacci number 100 going up and the other at 1 going up and so on, unless you already know the answers, which would kind of defeat the purpose. So that's a program where you don't benefit from having more processors because the critical path is the important part of the code that you can't parallelize. So when you try to figure out how much good parallel processing is going to do you, then you can, that's what we get these laws like Amdahl's law, trying to figure out how much benefit we'll get. So here, for example, we had this thing called count elements, which I think is the one that would have a long array consisting of digits 0 through 9, and you're going to count how many times each of those digits occur. And so you have, on one processor it takes 0.3 seconds, but on 2 processors it's 0.2 seconds, and 4 processors is 0.14. So this is pretty much the situation we were talking about. Quadrupling the number of processors cut the speed about in half. So this looks like around 50% efficiency, and here they go. They show 84% efficiency at 2 cores, 59 at 4 cores, 39 at 8 cores. So you see, you do get a speed up, but you don't get the optimal case speed up. So here's Amdahl's law. S is the fraction of the program that's inherently serial, and P is the part that can be parallelized. So if you add more cores, obviously, the total time is going to be this fraction of the time on one core, and this fraction sped up by a factor of C. This would be the 100% efficiency improvement. This is important. Reminds me of many other things like chemistry. If you have any kind of multi-step process, you can only improve one step, then you can't improve anything too far. The point is that more cores will speed up the parallel part, but you can't speed up the serial part. So you're going to hit a limit. And so here, for example, if the program is 90% parallelizable and takes 10 seconds on one core, then if you go to 10 cores, the serial time will always be 1 because the additional cores don't do you any good. The parallel time will go down by a factor of 10. So your speed up will go from 1 to 5 to 9.1, then 9.9. And even when you get to a huge number of cores, you're never going to get up to a factor of 10 speed up. Even if the parallel part took 0 time, your serial part would still be 1/10 of the code. So the maximum speed up you can ever get is a factor of 10. And adding more cores accomplishes very little. So this was Amdahl's analysis, and it made people feel like parallel computing was pretty worthless. And they kind of lost interest in parallel computing and focused for a long time on just making the clock rate of the single processor faster based on this kind of thinking. But then Gustav Barsis pointed out a different situation. Now, Amdahl considered, suppose I have a fixed problem, and I'm going to just try and take this one problem and spread it across many cores. He said, that's a sort of theoretical consideration, but that's not most common problems. Most common problems are different. What they do is they have a huge problem, and they're going to increase the problem. So the question is, I have like millions of records to process, and I'm processing 1,000 a day. Could I process 2 or 3 or 4,000 of those records by having more processors in a day? And of course you can. He says in the real world, you consider expanding the problem as you add more cores, and the total time is what's constant. And you ask, how many records am I passing through in a fixed amount of time? So this is just, it's not any different fundamental logic. It's just showing that this is probably a more realistic description of many real-world cases. So a program is scalable if adding cores improves performance. It's strongly scalable if you can improve performance for a fixed problem size. But I think, oh, by the way, I think this should say weakly scalable. I think it's weakly. I'll check. It's weakly scalable if you can add cores and increase the problem size, and that improves performance. And this is, of course, almost always true. If you had one computer working on your pile of data, and you got 2 computers to work on that pile of data, you'd think it would go twice as fast. If you could put another pile of data in the second computer, and that's the point. And this is the case in the real world, typically, you have. So anyway, that revived interest in parallel computing. And of course, the answer is pretty simple. I mean, the point is parallel computing can benefit you for some problems, but not for others. So here's some general rules. There's always some random fluctuation due to other processes on the machine, so run a program multiple times when measuring performance. Try to figure out where you want to measure timing. Think about, do you want to really go from the start of the program to the end, or do you want to skip certain parts, like where the user enters data or where you read it from the disk and only focus on one part? You decide exactly what you care about. Your hyper-threaded cores, you should be aware of, they probably don't really have as much performance as completely independent physical cores because they're sharing some resources among the hyper-threaded cores. So when you're counting cores, those cores may be less valuable. And of course, resource contention. Other processes running on your machine may slow the one you're testing. You might want to stop the other processes or build another machine with less background processes running on it or something to get a clean measurement of how the performance of your process you're testing. So then, of course, there's the problem of cache coherence. We've talked about this quite a bit. There are so many caches at many different levels in the machine, and the problem is those caches have data, and the data keeps getting out of date, and then you have to update it, and that's expensive. So your data is transferred in blocks, and the blocks are in sets, and the sets have lines, and each line has a single block of data. So a cache hit occurs when you find the data you need in the cache, but the problem is a cache miss when you don't find the data, and you have to perform a lookup at some other level of the memory hierarchy, which is slow. And so you have the valid bit that indicates whether the data at this line is safe to use. And so there's 2 strategies we talked about before to keep the cache synchronized with the main memory. And that's, you can write through, so every time you do a write operation, you do 2 write operations. You write to the cache and you write to main memory. That, of course, will slow you down by about a factor of 2. Or the write back strategy, which is more popular, where you write to the cache, but you only write it to the lower levels, like the disk or the RAM, when you have to, when the block is evicted. So you postpone that, so you can do multiple writes to the cache and then only write the cache once to main memory later, making it faster. So That's a cache coherent strategy. So here you got core 0 and core 1 on a 2-core computer running the same program, and the program has a local variable, x and g, and g is actually a global variable. So x is a local variable, but g is a global variable. So here it does some calculation and changes g to 5. Here it does a calculation and changes g to 10. And the question is, what should g be down here? And here's an example. This sets g equal to 5. Other things happen. This one sets g times 4. And this one, they do various calculations. Core 1 does other things. And x, so they're both changing this variable, and so that's a problem. If you don't have a cache coherence strategy, you're going to lose control here. These programs are going to have different copies of this variable with different meaning, a different value, and you're going to get the wrong value added up there. So you save this with the modified shared invalid protocol, and the technique for this is snooping. So this core will sniff on the write operations going on here, and if this one is writing to G, it will notice that and mark its cache invalid, saying, well, somebody else has been writing in here. I better not trust this value anymore. Next time I want to use it, I better refresh it from the main memory. And that's the game. Now that means you will have serious efficiency problems. And they call this false sharing. So here is count elements. This is the one I just talked about before that will count how many times a certain digit appears in a long list. And here's the root of the heart of the program. It's going to go through from start to end and find the value and then add that to the counts. And the problem in the early version of this program is we would have many threads running all with this same global variable counts. And so one of them could increment it, but then the other one could override it with another number that was smaller before it finished. So you ended up missing some of them. And that's what you saw here. And the other thing, so that not only did this give you the wrong answer, this version of a parallelized program, it actually gets slower when you add more cores. 0.3 seconds at 1 core, 0.8 seconds at 2 cores, 0.8 at 4 cores. And the reason it gets slower when you add more cores is because the first thread will read the array, then it will increment the count, and this invalidates the cache line over here. So this one's going to read the array and have to go to the main memory for it. This one's going to read the array. This will increment this one, invalidating the cache line. This will be invalid. So you're really constantly having to refresh it from main memory. You're not getting any good out of the cache. In fact, I call this thrashing. You're constantly reloading the same cache block over and over and over. Your attempt to make it faster with caching is in fact making it slower with caching because you're moving a whole block of data like 64 bytes every time instead of just going to like one global variable and doing one read and write on it every time. I'm pretty sure this happened to me. About 8 years ago, I did a capture the flag contest, and they had programs you had to write, which I did a lot of them, but then they said to get the next flag, make your program 10 times faster, and then make it 10 times faster again. And I tried to write multi-threaded code, but my multi-threaded code was not any faster, and I gave up. I didn't know how to do this stuff. But it's not as easy as you think. All right, so they call that false sharing. The code, you think you're accessing a shared data like a global variable, but in fact you're doing something much less efficient. You're constantly copying that variable and a bunch of extra data back and forth into the cache, wasting a whole lot of read and write operations, making you slower. So if you want to fix that, one thing they say is to pad the array so it doesn't fit in a single cache line. That's a pretty terrible idea. But if each one of them was in a different cache line, then they wouldn't be invalidating each other so much. That's unlikely to work. What's much better is to just use local storage, which we talked about before. Don't keep trying to increment the shared variable. Instead, have a local variable with the counts and add those up, and then just once lock the global variable right into it and unlock it using mutex, like we said before. This is a much better way to do it. Then this part can run independently on every core, and it's not going to collide with anything. And this part can have the mutex make sure that you don't have threads undoing each other's work there. All right. And then there's thread safety. It turns out, amazingly enough, some C library functions are not safe to run in multiple threads. Very interesting. A function is re-entrant if it can be re-executed, partially executed by a function, but it turns out that some re-entrant functions are still not thread safe, which I guess means they must share something in some shared variable that they assume is not changing due to any other process. That's the most likely reason something would not be thread safe. It may be something more subtle than that. But there's a web page that lists the thread unsafe functions. And the thing I noticed is I don't think I've ever used any of these functions. The only one I've ever used, I think, is random. And everybody warns you not to trust rand too much. But I guess rand, in addition to its other flaws, is not thread safe. But anyway, I was glad to see these are pretty obscure functions that I don't think I've ever used. So we can use string talk here. Now, string talk is something that converts strings to tokens. It reminds me of the split function in Python. You have an input string with a bunch of numbers separated by spaces. And so if you use string toke here on a space, it'll find the first element using a space as delimiters, as a string. And then if you run it with null and a space, it'll find the next element. So this is an easy way to pick the elements one by one out of a single string that has a whole series of elements in it. And in this case, those elements are going to be numbers. You need to use those numbers and count how many times the numbers appear. So here it is running, and it works. If you have 100,000 elements, then you get about 10,000 in each bin, which means it's working all right. All right, now if you make the multi-threaded version here, where instead of going through the entire string, you go through part of the string. So I'm not quite sure how I see how that works. Input string plus start. Somehow they picked a part of the string here to work on for each thread. And so you have mutex lock. If it add the totals in, and off you go. And now it gets tremendously wrong numbers. With one thread, you get 10,000. With two threads, you get 500. So it misses most of them. And with four threads, you get 5,000. So it's terrible. Even though your code is written in a way that's thread safe, the string talk function is on that list of forbidden functions. It's down here, string talk. String to token is not thread safe. So even when you try to make it thread safe, it's not. That's a thing to know. So if you replace it with string talk _r, which is thread safe, then you'll get the right answer. So that's a thing to know. And the last bit is that there's easier ways to do threading. The way we've done it here, you have to do things like mutex lock and mutex unlock, and that it can be pretty ponderous. OpenMP makes that easier. It's implicit threading. What we've been doing up till now is explicit threading, where you have to code every little lock and such, and that turns out to be very painful to get right for big projects. That's POSIX threads. So this one here, you use pragmas to just mark parts of the code. So pragma OMP parallel will create a team of threads and you can set these variables, a number of threads, variables that are private, variables that are shared, and default indicates whether you should leave them up to the computer. You almost never want to leave that, so you use default none to make sure of that. So you can specify which variables are private and shared just up here, and then the code in that region will be interpreted that way. It'll automatically add whatever directives are needed to make that happen. Here's one that will do a for loop. And here's one that will make a parallel for loop. It'll create a team of threads and run a for loop. It doesn't, by the way, work for things like do while loops and stuff, just for for loops. And here's how you mark the critical section. This is the critical section. Only one thread should execute it at a time. So this is much friendlier for the programmer. And there are useful functions. Here's a function that will get the number of threads. Here's ones that will set the number of threads. Here's one that will get the thread number of the currently running thread. So you can figure out which thread you are in case you want to know that. So here's the simplest one, hello world. Here's hello thread. So it's going to include the omp library. And down here, it's going to run omp get thread to get its number. And now it's going to say, hello world, I am thread number, that number. And here in the main function, it will get the number of threads as a command line argument. And then it will have this pragma, omp parallel num threads. So it'll spin, you put the number of threads right up here. So it'll spin that many threads up and run hello world on that many threads. And so you'll see if you run it on 4, you'll get 4 threads that, of course, come through in a random order. So this is much easier. All you had to put in was about 3 lines. This include this pragma, I guess just 2, and then this one here, getting a thread number. So that's pretty friendly. And a more complex example is count sort, the one I talked about where you have a list of single digits, and you're going to count how often each of those digits appear. So in main, I'm going to count elements and then write the array. And counting the elements is the part I'm going to talk about here. Here's the pragma omp parallel. No defaults, And these things are shared, and apparently the others are private, even without explicitly saying so, which is interesting. In fact, let me check. I wonder if I just cut that off. Let me check the textbook. I don't have a hands-on project for this stuff, which would be nice, but I don't have one yet. Just something I would like to try. This is 14. Okay, let me make this smaller so I can, there we are. All right, so it's 14. This one, it just occurred to me, maybe I missed part of that line. There. Nope, I didn't miss it. That's what surprised me. Okay, I'll go back to my slides. They're correct. So, apparently, you can just say the shared elements and the other variables you define down here are interpreted as local. That's interesting to me, and I'd like to know more about that. But anyway, so val and I and local are just local. And so you've got this part here is now going to be parallelized easily. And this is going to use, this is how you do it. Instead of having mutex lock and mutex unlock, you just mark it critical, and it will note only that one thread use this code at a time. All right, and so the results are, not only does it get the right answer, but you get really high quality speed up. One thread is 0.24, two threads is 0.12, four threads is 0.06. That's almost 100% efficiency, which is really nice. So this OMP thing appears to be great. All right. That's what I wanted to show you. Let's try a Kahoot, which is here. All right. All right, so program runs 10 seconds on 2 cores, but 5 seconds on 4 cores. What's its efficiency? You know, I think I should have had 10 seconds on 1 core there. Mistake in my question. Yep, sorry about that. That's a mistake in my question. It's really 0.5. This one is running at 100% efficiency. If you double the number of cores and it goes to half the time, what I meant to say here is 1 core. That's a mistake in that question. Very annoying. Error in first question. Good thing these are extra credit, because I do make mistakes sometimes, and I made a mistake on that question. Anyway, not like it's going to matter today. If there's only 3 people competing, you'll all win. All right, so which item makes sure that each cache maintains a consistent view? That is the MSI protocol. That's the protocol that marks areas shared, invalid, or modified, something like that. And so you can tell which ones have been modified and refresh them from the main register. This is what prevents you getting inaccurate data in the caches and trusting it. All right, which technique uses these pragma statements? Yep, that's OpenMP. All right. So I think there's only 3 contenders, so it's not a surprise who's winning. All right, good.